My dear people, in this particular section, we are going to look at how to suck fuel out of a car. Please don't do that. Please don't do that. Yeah. Unless and until you're a trained mechanic or if you're doing it for some sort of a proper reason. Okay, now, my dear people, all fun aside, siphoning or siphon, as one of my friends from Paris calls it, but we'll call it siphoning. So siphoning is a typical Bernoulli's principle problem. Yeah, and during your lectorial next week, I'll try to do a small demonstration with siphoning. Okay, so what do we have here? So a siphon is installed in a tank. Okay, that's good. The diameter of the pipe is 15 centimeter. So the diameter of this pipe is 15 centimeter. Always make sure that you convert it into meters. Okay, it is used to suck an oil of relative density zero point 0.8 from tank 1. So this is tank 1. Yeah, and relative density of zero point 0.8. What is relative density? Huh? Exactly, density of a liquid with respect to the density of water. Fantastic, fantastic. Yeah. And what is the density of water? What? Exactly, 1,000 kilogram per meter cube. Okay, so this oil has a relative density of zero point 0.8 and it is open to the atmosphere. Okay, so P1, the pressure at section 1, I can just take it to be atmospheric pressure, P atmos. Okay, the tube discharges to the atmosphere at an elevation of 1 meter. Okay, so the tube is also discharging the fuel out. Someone is sucking the fuel out. Okay, it is discharging to the atmosphere, which means P3, otherwise the section 3, the pressure is also atmospheric pressure. That's very good, and we know that it's an elevation of 1 meter. Z3 is 1 meter. The oil surface in the tank is at an elevation of 4 meter, so Z1 is 4 meter. What they're saying is the center line of the tube is at highest at 5.5 meter, so section 2 is 5.5 meter. They are asking us to calculate the discharge through the exit, otherwise the volumetric flow rate through the exit. If you think of it, whatever volumetric flow rate is going to be here is exactly the same volumetric flow here and also in this particular section. Continuity equation. Yeah. And also they are asking us to find out what would be the pressure at this particular point 2. Yeah. Okay, let's see how to solve this problem. I've just highlighted all the important bits. Yeah, people, if you're not sure about the question, I would suggest that you go back and just have a look at this problem again. The first thing is, I know that zero point 0.8 relative density is kerosene. You don't need to have it. You don't need to know that. I just know it, so I've just written. So the relative density of the fluid here is zero point 0.8. So relative density equals the density of the fluid divided by density of water. But here we need the density of the fluid. So density of fluid is density, relative density times the density of water divided by, goes to the other side and becomes times. So zero point 0.8 times 1,000 is the density of water, so 800 kilograms per meter cube. It just means that if you have a tank of water and then if you pour this particular fluid on the top, it is just going to be floating, it's not going to sink. That is what it means. Yeah. And one more thing, P1, thus the pressure 1 and pressure 3 are atmospheric pressure. So the gauge pressure is 0 bar. Yeah, atmospheric pressure is 1 bar. The gauge pressure is approximately 0 bar. Yeah, fantastic. The volumetric flow rate and the pressure 2. Okay, in order to find the volumetric flow rate, we need the velocity through which the oil is flowing through the pipe. And since they are asking at section 3, I've just written that v dot 3, the volumetric flow rate at 3 equals area 3 times the velocity 3. Continuity equation. So in order to find C3, I'm putting in the Bernoulli's equation. For I'm applying Bernoulli's equation between section 1 and section 3. I'm not looking at section 2, just section 1 and section 3, because according to Bernoulli's equation, the energy should be the same. Yeah, no matter what. So Bernoulli's equation P1 by rho g plus C1 square by 2g plus Z1. Yeah. So here I have cancelled out P1 and also P3 on the other side, because I've just told you, the gauge pressure is approximately as well almost zero. So I've just cancelled them out. Yeah. And also I have cancelled out C1 square by 2g. What is the reason? The reason is, look at this, the velocity with which this oil is going to go down is going to be so very small compared to the velocity with which the oil is going to flow through this pipe. Yeah, because of the large surface area, the velocity is going to be very negligible. So I'm assuming it to be zero, so I'm just cancelling out. So the only thing that I have between section 1 and section 3 is Z1 and C3 square by 2g, plus this should be Z3. It should not be Z2. It is a mistake I've made. I could have easily like re-edited the video, but I'm not going to do it because I want you all to know how easy it is to make a mistake. Yeah, because I'm applying for section 3, this should say Z3, shouldn't it? Yeah. And also I want you to know it's not just students, even academics make mistakes. Okay, if you think of it, we know Z1, we know Z3, we know G, the only unknown is C3. So I'm going to substitute everything that we know. Again, this should say Z3, not Z2. Yeah, it's a mistake that I've made. And rearranging the equations, I get C3 equals 7.67 meters per second. So otherwise, that is the velocity with which the oil is flowing out of section 3. But if you think of it, my dear people, the diameter of the pipe is exactly the same everywhere, and the volumetric flow rate is going to be same everywhere because of continuity equation, which means the velocity C3 is equal to velocity C2 in the pipe. Yeah, we'll go to that in a minute. Yeah, so after finding C3, I'm using continuity equation to find the volumetric flow rate, because that is what they're asking us to find. Yeah, v dot 3 equals a3 c3. A3 we can easily find because the diameter is 15 centimeter. So the area is pi by 4 d square times the velocity which we have found, and the volumetric flow rate I know. Yeah, so now I have found out this one. Now how to find P2? Again, very simple. I can apply Bernoulli's principle between section 1 and section 2. Can I not? If you want, you can also apply Bernoulli's principle between section 2 and section 3. Yeah, that's also possible. But I have applied it between section 1 and section 2. Again, I have cancelled this out because the gauge pressure is zero, and also the velocity with which the fluid is going to flow in the big tank is negligible, so that is also I've cancelled out to be zero. So here I know Z1. Yeah, I know rho and g. I know C2. I have because as I told you, C2 and C3 are exactly the same because of the continuity equation. Yeah, as the tube is the same diameter and also the volumetric flow rate is the same. So C2 is C3. I know this. I also know Z2. So all that I have to do is substitute everything in the equation and find the only unknown, which is P2. Yeah. Look at this. So 0 plus 0, Z1 is 4 meters equals P2 by rho g plus C2 I know is 7.67 squared divided by 2 times gravity plus the elevation 5.5. All that I'm doing is just simplifying the equation, and I get the pressure to be negative 44.1 kilopascals. My dear people, look here. I would like you to pause, yeah, and try to work this problem on your own. And look at this, look at the step by step I have made to see how I have simplified the equation. Is that okay? Yeah, fantastic.